Here we go with topic 7 on hybridization and sigma and pi bonds, and this is in unit 2 on molecular and ionic compound structures. We're still focusing on the molecular structures in this section, so our covalent compounds. So we're going to use the 3D shape of our chemical to determine its hybridization of our orbitals and how sigma and pi bonds, how many the compound has. So let's start with hybridization. A hybrid orbital is a combination of s and p orbitals of the central atom to create new electron orbitals that are all equal. So atoms bond by sharing electrons from their s and p orbitals, their valence electrons, since these are their valence electrons. However, our s and p orbitals are not equal in energy. It is observed, however, that a central atom has equal bonding around it. So this means that all the orbitals that are being used to bond must be equal. So something has to happen with our s and p orbitals to make them equal. And what happens is called hybridization. So we're going to use carbon as our example to analyze what's going on here. And carbon is a perfect example showing the need for hybrid orbitals. So as we have seen before, carbon's ground state electron configuration is shown here. We have 1s2, 2s2, 2p2, and we've got its electron diagram there as well. So this is the electron configuration for our carbon. It would have these 4 valence electrons. It's s and p orbitals of the highest energy level. Now, if carbon right now only has 2 unpaired electrons in those p orbitals, it might be assumed that it would only bond twice. But we've seen from all of our structures we've drawn and chemicals that are produced from carbon that it tends to bond 4 times, and that all of those bonds are equal to each other. So its orbitals must change in order to accommodate this. These s and p orbitals have to change around. So what happens? One electron from our 2s orbital, so one of these guys up here, is promoted to the p orbital. So it moves to our p orbital so that they're all unpaired electrons, and now they can all bond. So this is now what our electrons look like. And then those 4 orbitals, so your s orbital and your 3p orbitals, hybridize to form 4 equal orbitals, and we call them sp3 hybridized. So basically, instead of having our s orbital, which is that spherical shape, and our p orbitals, oh, that is a terrible drawing of that, our p orbitals that are kind of this dumbbell shape or this peanut shape, with their 3 different directions, one along the x-axis, one along the y-axis, one along the z-axis. All 4 of these things, it's like we squish them together and then we come up with a new orbital and divide it by 4, and they're all the same. So each of these becomes this new shape, and they're kind of a mix between the two. It's kind of got this almost spherical side and then this larger dumbbell side. So we would have that, but 4 of them. We call them each an s, and or we call them all as a group the sp3 orbitals. So 1 s and 3 p's make up our sp3 hybrid orbitals. And now when this orbital overlaps with another element, we have equal bonding. So an example of that might be creating CH4, right? We don't find that any of these bonds are different from each other. They're all the same. They all take the same amount of energy to break the bond. So that means that the way they're sharing these electrons must be equal to each other. So the orbitals that are overlapping to create those bonds must be equal to each other. We call those sp3 hybridized orbitals. sp3 hybridization. So a little bit more on this type of hybridization. sp3 hybridization can explain the tetrahedral structure So just our tetrahedral structures of molecules, as well as structures derived from the tetrahedral structure. So those ones that are all related. In it, the 2s orbital and all three of our 2p orbitals hybridize to form 4 equal sp3 orbitals. When an atom has 4 electron domains, bonding or non-bonding, it will have sp3 hybridization. So this will apply to any of our tetrahedral, pyramidal, or our bent structure with those 4 electron domains. So again, here's a nice picture of what I was trying to draw on the last slide. So these 4 orbitals are s orbital, and then the 3 different p orbitals each hold 2 electrons. And when all of these kind of morph together, they create 4 new orbitals. They're all turned in different directions. Each of those holds 2 electrons, so we still hold 8 electrons, but now they're all equal and the same shape as each other. And those are our hybrid orbitals. So they are all called sp3 hybridized orbitals. So this type of hybridization will work for tetrahedral, pyramidal, or bent structures with 4 electron domains. sp2 hybridization can explain the trigonal planar structures of molecules. In it, the 2s orbital and 2 of the 2p orbitals hybridize to form 3 equal sp2 hybridized orbitals. So when an atom has 3 electron domains, bonding or non-bonding, a total of 3, it will have sp2 hybridization. So this applies to any of our trigonal planar structures, and it would apply to that bent structure that's created when we have 2 bonds and a lone pair on our atom. All right, that would also can be sp2 hybridized because we have 3 electron domains. So if we take the same type of thing, we're taking that s orbital and 2 of our p orbitals, putting them together, we get sp2 hybridization, and we get these new shapes that are formed in equal bonding surrounding our atom. Our last type of hybridization is called sp hybridization, and it can explain the linear structure in molecules. In it, our 2s orbital and 1 of the 2p orbitals hybridize to form 2 equal sp hybridized orbitals. So when an atom has 2 electron domains, again bonding or non-bonding, it will have sp hybridization. So this applies to any of our linear molecules. So we're taking that one s orbital, we're taking 1 of those p orbitals, and again combining them to form our sp hybridized orbital. So let's try out identifying the number of electron domains around our central atom and then relating that to the hybridization of that central atom. So we're going to find the total number of electron domains and then figure out the hybridization from that. So around this central carbon, we have 1, 2, 3 electron domains total. And so for that, we would need that s orbital, and then we would need 2 p orbitals to give us 3 orbitals to hybridize and give us our 3 electron domains that we need to bond in this molecule. Our next one, around our central carbon, we have 4 bonding domains, so 4 electron domains. So we would need an s orbital and 3 p orbitals to give us 4 orbitals that hybridized to accommodate all of our electrons. So it would be sp3 hybridized. Our next one, our nitrogen, has 1, 2, 3, 4 electron domains. We count a lone pair on the central atom as an electron domain. So it has 4. So again, it would need the sp3 hybridization to accommodate all of the electrons. And last one, around our oxygen, we have 1, 2, 3, 4 electron domains again. So again, it is sp3 hybridized. So we can see that each of these with 4 domains are all the same hybridization. And it's all because they are related back to this tetrahedral shape because they all have those 4 domains, so either bonding or non-bonding. If you had a central atom with just 2 domains, those 2 domains would cause it to be sp hybridized. We need that just one of our s orbitals and one of our p orbitals to accommodate our electrons. Here's a summary of what we looked at. So if we have 4 total domains, it will have a shape that's either tetrahedral, pyramidal, or bent, and all of those will be sp3 hybridized or have sp3 hybrid orbitals. Something with 3 total electron domains, either trigonoplanar or that other bent shape that only has 1 lone pair, then it will be sp2 hybridized. And if there's 2 total domains, it will be linear and it will be sp hybridized. So just to tell the difference between these 2 bent structures, this is bent with 2 lone pairs, and this is bent with 1 lone pair. But you can always just count your number of total domains and then relate the hybridization to that. We are now going to take a look at sigma and pi bonds. So sigma and pi bonds are another way of describing where the electrons are likely to be found when bonding between 2 atoms. This comes from a larger theory called molecular orbital theory, but that part is beyond the scope of this class. So we're going to focus on sigma and pi bonds, which are in this class, are part of the AP curriculum, and how we identify them. So sigma bonds are represented by this symbol here. That's a lowercase sigma. You might have seen uppercase sigma in your math class. We're going to use it later this year. It's that uppercase E looking character. But lowercase sigma, these sigma bonds are when the electrons lie along the internuclear axis between 2 atoms. This means that if we draw a line between the nuclei of 2 bonded atoms, the electrons would be found along that line. So if we had 2 atoms that were had their positive nuclei, if we could draw a line between those nuclei, the electrons would lie along that line, and we call that a sigma bond. So each single bond is made of 1 sigma bond. So if we looked at this CH4, this methane molecule, each of these single bonds in it we would call a sigma bond. So this has 4 sigma bonds. And it's kind of like a little O with a little line going off of it. Our water molecule here has 2 single bonds, so we would have 2 sigma bonds. All right, so each single bond is 1 sigma bond. The other type of bond is called a pi bond and represented by our symbol pi. You guys are probably familiar with. So pi bonds occur when the electrons are above and below the internuclear axis between 2 atoms. And they occur when atoms are either double or triple bonded. So if we imagine our 2 carbon atoms that are shown below, they would have a line connecting those 2 carbon atoms at their nucleus. That would create a sigma bond, like we talked about before. So this central bond here we would call the sigma bond. But our electrons would also be overlapping in their orbitals, so let's call them the orbitals. They would be found between the atoms both above and below that axis, that internuclear axis. So we call that a pi bond. So each of these would be called a pi bond. So our triple bonds, the other 2 bonds that are created between our 2 carbon atoms, are called pi bonds. So each carbon atom has 1 sigma bond with each hydrogen. So those are, I'm going to circle those in yellow, all of our sigma bonds. And then the 2 carbon atoms share a triple bond. One of the triple bonds is our sigma bond in the middle there, and the electrons lie between the atoms. The other 2 bonds of the triple bond are called our pi bonds. So this structure would have 3 sigma bonds basically one for each type of bond we have, or each bond that we have, and then it would have 2 pi bonds. All right, and that just gives a little clarity on a molecule and saying what types of bonds are present on this molecule. All right. So to summarize this, if we have a single bond, we have 1 sigma bond and 0 pi bonds. If it's a double bond, it consists of 1 sigma bond and 1 pi bond to create the double bond. If it is a triple bond, then it consists of 1 sigma bond and 2 pi bonds to create that total of a triple bond. So let's take a look at counting how many sigma and pi bonds are in each chemical. So this is the type of question that might be asked on the AP test, typically a multiple choice question. It might ask which chemical has pi bonding or which chemical has a certain number of sigma bonds, that type of thing. So we just need to be able to identify them and count them. So for our first chemical here, we have 2 single bonds and then a double bond. So one of those would fall into our sigma bond category. So we have 3 sigma bonds, and then the second bond of our double bond would be our 1 pi bond. All right. In this next structure, we have 3 single bonds, so we would have 3 sigma bonds. And then we have no doubles or triples, so we would have 0 pi bonds. In our last structure here, we have 1, 2, 3, 4, 5 of our single bonds plus 1, 2 from our double and triple bond. So we have a total of 1, 2, 3, 4, 5, 6, 7, 7 sigma bonds in this chemical. Our double bond, the second bond in that would be a pi bond, and the other 2 bonds in our triple bond would be pi bonds. So we would have a total of 3 pi bonds in this larger chemical. So that's how we can analyze these structures. This is the basic type of question they would ask on this. Same thing with our hybridization. They would ask you to identify what the hybridization is on a particular element, or ask you which element has which compound has a particular type of hybridization, sp, sp2, or sp3 hybridization. So you've got some practice on your paper. It does help to draw the structures so that you know how many bonds it has, lone pairs, all of that, to be able to identify your type of hybridization and your types or your numbers of sigma and pi bonds. So definitely draw them so you know how those structures look. All right, let me know what questions you have. Thanks, guys.